Hello. Here's a quick video on friction. So first thing you're gonna do, take the little wooden block, um, mark what side is up so you can remember what side is sliding on the wooden ramp you'll use here. So you're going to have this block be pulled, it's going to slide. So mark what side's up so you know what side's slid. You're going to weigh this with your little digital scale. You're also going to need the 500-gram mass, which you're going to assume it's correctly stated because our little scale can't weigh it. So that's, you're going to have these two masses, and then you're going to take your little spring scale and we're going to pull that along the ramp. So the instructions show you how to zero this thing out. You can slide this up and down and then line it up with where the zero and the indicator are the same. So there's a reflection. There we go. Right there. So that is now zeroed or taired. You're gonna hook it on the block and start all the way to the end, so you got as much ramp as you as much ramp as you got to pull. And then you're gonna start pulling it and get it at a good speed. Nice, slowly increase your speed until it starts moving, and then maintain that speed, and then record that measurement. That will be FK for trial one. So trial one, FK, whatever this thing read in newtons from 0 to 5 newtons, that is trial one's FK for kinetic, force of kinetic. Kinetic meaning moving. Do that 3 times, get 3 different FKs for, and this is for flat. We're going to turn this thing on the side here in a second. And then you're going to do the same thing again, except now pay attention to whenever the block at its very, very first starts to move. So and probably look at the scale and then use your peripherals to see when the block starts to move. And when the block starts to move, try to see where that number is when it starts to move. Show this up here. So do what you were doing earlier, same speed increase, and when it starts to move, what was that number? So if you do it smooth enough and pay close enough attention and it just works well enough, you should notice that there is a higher force required to get the block moving than there is to keep the block moving. So try to see if you can notice that little bit of a higher force on the scale, and that's going to be your FS for static. So that's the force required to get the block moving. Static from being still, however you want to look at that. So you'll do that 3 times, record FS trial 1 through 3 in newtons from the scale. And then you're going to do the exact same thing where you turn the block on its side and do it all again. Okay. So now, I don't know if I clearly stated what weight is in the data table 1. So weight is the weight of the block and the mass. So we got the mass of each of these, but the weight is its mass times gravity. So in your calculator, and make sure you're in kilograms because gravity is 9.8 meters per second squared. It's already in, or we're going to be in newtons. Newton has kilograms in it. So we had 500, and my sample data has 28.4 grams for the wooden block. Should probably share my screen. So here's what I was looking at. I should have shown you. There's the weight of our little wooden block. Then take the weight of the wooden block plus the weight of the mass, 528.4. Get that in kilograms, so 0.5284 times it by gravity, 9.8. And that's where they get the little 5.18 for weight. So the weight in this orientation is 5.18 newtons, and the weight is its force, its gravitational force. When you put it on the side, the mass of the wooden block doesn't change, so it's the same number. So 5.18 all the way down that column. Then, like we were saying, do the trial 1 1.23 for kinetic. Do the same thing for static. You can see this is higher than this. All of them are. To take the average of them all, get these, and then to get the coefficients, it's this force. So the frictional force is the normal force times the coefficient. So to get coefficient by itself, divide both sides by the normal force. The frictional force divided by the normal force will give you the coefficient. That's where this formula should be here somewhere. Yeah, that's it right here. Force from the spring, which is these forces, divided by the normal force. So divide 1.19 by 5.18 and round it up to 2 decimals, and you get 0.23. That's how you'll complete data table 1. For data table 2, drop this down some. I think you start, let's see. So this you'll use the 100-gram weight, LC to 50. So this one you're actually changing the normal force. So at last one we used the 500. Here you'll place the 100, and then you'll place the 100 and the 50 to do 150. So, and then again, get static and kinetic frictions for each. So just like we did for data table 1, except now instead of 500, do it with 100, and do it with 150. And then for part 3, you're going to change the material of the block. So you put a piece of paper on the other side. You have a block that has like sandpaper on it, and you got a block that has a mirror, or I guess you'd call it glass, whatever you want to call it. And then they also sent a little piece of packing material. I'm sure there's a better word for that, but to me it looks like they cut up some from Amazon. So for that one, same thing, different surfaces for your blocks. For part 4 is kind of neat. You'll see which one they want you to use. Take the wooden block. So take this wooden block, and then you're going to slowly increase this angle until the thing starts to move. When that block starts to move, if you go back a couple chapters in your lecture, you have a block on a ramp. There is the force from mg, and then the normal force, but the force from mg can be broken down into 2 components. One that takes this block down the ramp. Well, whenever you get this ramp increased to the perfect angle, the block starts to slide, you have found the force that is the force that you found earlier from pulling with the spring scale to start the block moving. So you can find the kinetic coefficient just like you did in part 1, but now you wait till you find the angle. And then I think I shared a document showing the math where this formula comes from. So you go back a couple chapters in your lecture, you put the block on the ramp, do force by diagram, do Newton's second law for both directions, solve for mu, and you actually see that mu is just inverse tan of, which I don't show it there. Where's it at here? Oh, yeah, sorry. Yeah, the angle is inverse tan of the coefficient. So you can quickly, not quickly, but find that value. So yeah, on this one, they actually want you to solve for what the degree should be. So get a little ahead of myself there, or got ahead of myself there. So you could solve for what the coefficient was, but instead of that, you're going to solve for what is the angle before the thing should start sliding, and then you'll actually do it and make that measurement and compare what the angle should have been, which is this formula, to what you actually measured with your protractor. So that's what you'll calculate a percent difference with. So that's it for friction. It's a lot. So let me know if you have any questions.